Okay, this is part 2 of our discussion of units and significant figures. So, the rules for how we count significant figures. First, all non-zero digits are significant. So, for example, 123.4, well, none of those are zero, so they're all non-zero, which means it has 4 significant figures. Okay, 0.012 has how many non-zero digits? Hopefully everybody said 2, so it has 2 significant figures or significant digits. Okay, second rule, interior zeros. So those are zeros that are between 2 non-zero digits are significant. So in this case, since the 0 is between the 1 and the 2 in 102, it has 3 significant figures. So 1.002, both of those zeros are between non-zero digits, so it has 4 significant figures. Okay, leading zeros, which are zeros to the left of the first non-zero digit, are not significant. So in this case, our 2 zeros are before our first non-zero digit. So they are not significant, they're just there so we know where the decimal point is. So 0.012 has 2 significant figures. Okay, by the same reasoning, 0.00034 only has 2 significant figures. And that's because all the zeros are before the first non-zero digit. Okay, scrolling down to the next page of the notes. Trailing zeros. So zeros at the end of a number may or may not be significant. So if the trailing zeros are after or to the right of the decimal point, they are significant. So 12.00 has 4 significant figures because those zeros are significant because they're to the right of the decimal point and they're trailing. 13.590 has 5 significant figures, 4 non-zero digits, and 1 trailing zero to the right of the decimal point. Okay, trailing zeros before a decimal point and after a non-zero number are significant. So 120.3 has 4 significant figures, and 4000.5 has 5 significant figures. Okay. Here's where we run into problems. Trailing zeros that are before an implied decimal point are ambiguous, and therefore we should avoid them by using scientific notation, and we'll talk about the scientific notation later. So 4,500 has an implied decimal point to the right of the last zero. So this, we can't say how many significant figures it has, so we'll say not applicable, and that's because it's ambiguous. Which means we can't tell one way or the other which are significant and which aren't. Okay, so 2 and 3 are both examples of scientific notation that we will talk about later. But when we have significant figures in scientific notation, we do not worry about the times 10 to the power. We just look at the first number. So 4.5, hopefully everybody by now knows that that's two significant figures. And 4.50 times 10 to the third, remember we just ignore the 10 to the third power. And we look at 4.50, and that has three significant figures. So the only other thing we have to look at is what we call exact numbers. And the exact numbers have no uncertainty. They're exact. So that means they have an unlimited number of significant figures. They can have as many or as few significant figures as we want. So for example, if we have 3 students in a classroom, 3 is an exact number, so it does not have a significant figure value because we could write it as 3 or 3.0 or 3.00, etc. So we can give it as many significant digits as we want. Defined quantities are also considered exact numbers. So for example, 100 centimeters equals 1 meter. That is a defined value, so the value of 100 centimeters does not have a significant figure designation. But it's not ambiguous even though we have that implied decimal point, because it is an exact number because it's part of a definition. So integral numbers in an equation, so numbers that are part of the equation, do not have significant figure designations either. So for example, if we have radius equals diameter divided by 2, that 2 is part of the equation, and that makes it an exact number. Now, why are these exact numbers important? Essentially, it's because exact numbers do not affect the number of significant figures when we do arithmetic. So, rounding with significant figures is no different than normal rounding. We round up if the leftmost digit dropped is 5 or more, and we round down if the leftmost dropped digit is 4 or less. So, rounding up, if I had 5.37 and I said round it to this place, then I look to the right. The 7 is the rightmost dropped digit. It is bigger than 5, so when I round up, and so where the 3 is, it becomes a 4. Okay, if I had 5.73 and I said round to where the 7 is, then we look one digit to the right, which is the 3. That's 4 or less, and so we round down, so the 7 stays the same. So 5.7. So we need to round the following to two significant figures. So first figure out where the second significant figure is. In this case, it's the 3. We always start at the left and count towards the right. So 2 significant figures is where the 3 is. And since we've already done it, that's 5.4 because the 7 makes the 3 round up. Okay. For the 5.64, 6 is the second significant digit. 4 means round down, so we have 5.6. 5.35, we're still looking at the 3 because we're doing 2 significant figures. And the rightmost digit that we're dropping is a 5, so we say 5.4 because the 5 makes the 3 round up. Okay, what about the last one? Okay, we need to go to 5.349. 2 significant digits is where the 3 is. And I'm sorry, I think I've said rightmost digit for all of these. I meant the leftmost digit that we drop. So the leftmost digit that we drop here is the 4. So the 9 doesn't matter. We only look at the 4, and the 4 is a round down, so we have 5.3. All right, that is the end of part 2 of units and significant figures. We will finish this lecture in the last video.